All right, everyone. Hello. This is Mrs. Martin here with today's notes on solving exponential equations. Now, before we start solving exponential equations, I think it's important for us to review some of our exponent properties. So to start, let's go ahead and add those to our notes. Review of exponent properties. Because if we're going to be manipulating equations, we should have a good handle of what our properties are. Okay, so the first one that we might want to be aware of is when we have the same base, then we add our exponents. So when we have the same base, they're being multiplied, we've got our product rule happening, and we're adding those exponents. Okay. Another property we might want to remember is when we have two of the same base being divided, our exponents end up subtracting. So that might be another one that we want to be aware of as we're working through these equations. To continue, we've also got our power to power rule, two exponents that are separated by parentheses. We're multiplying those guys. Okay, so we've got that one. We also might want to remember our negative exponent rule, which is what we get, which is when we get our reciprocals. A lot of you were really, really good with that. Same thing happens vice versa. Okay, it's just the reciprocal of itself. If it's got a negative exponent, it turns that exponent positive. And I think that's about all we'll need. We won't worry too much about fractional exponents for today. Those might come up later, but for now, we're good with these. Okay, so let's start out with our first example, and I'll do our first example over here on the right. When we started out today, we had the following problem. Okay, here's our first example. And so let's notice some things about this example. The first thing I notice is that we've got variables in the exponent. Not something we're really used to yet. We didn't have to deal with those before, so this is new for us, besides graphing them, of course. Another thing that I noticed is that they're base numbers. So if we forgot, this big number at the bottom is the base, and these guys up top are the exponents. Okay, so just as a reminder of some of our vocabulary, in this example, the base value is the same. So let's talk about something just for a second. If I have a to the m equals a to some exponent, what does that exponent have to be? Some of you might be understanding that it has to be m. I feel like Dora the Explorer. I'm just waiting for responses. Good job, it's m. Okay, it has to be m. If it's not m, then it couldn't be equal. A to the m equals a to the m. It's identity, okay? It's just what it is. So then again, if I gave you a cubed equals a, not sure, what would that have to be? That would have to be a 3. By nature, it's what equals means. It means it's the same thing on both sides. So knowing those things, so I'm just going to put that up in a box up to the side. So if we have two of the base values that are the same, 2 and 2, if those two are the same, much like a is the same base as a in both of these here, then that means their exponent has to be the same as well. by definition, okay, if m is equal to m and 3 is equal to 3, then 2x is equal to x plus 7, okay, by nature. So knowing that, I'll do this in blue, 2x has to be equal to x plus 7. Okay, that's just how exponents work. It's what they mean. It's what it means to be equal. And this one was pretty straightforward because our base values were already equal for us. So we can go ahead and solve this. Subtract x on both sides. 1x is left, and a 7. And we're done. X equals 7. So when we see variables in the exponent, it does become a little stressful. You know, it feels like, you know, if we're working with exponents, and the opposite of that is roots. So do we have to do some sort of root there? Is there something that we don't know about? And we will be talking about that after spring break. There is an inverse property for exponents. But for right now, our focus is to try to puzzle out these examples so that our base values are the same, much like these two 2's are the same. That way we can just focus on the exponents and solve for that variable. Okay? So instead of stressing when you see exponents, just carefully try to break them down as much as we possibly can. Let's try another example where we don't have the same base on both sides. Okay, so here's example 2. Okay, example 2, let's do 3 to the x power, and then let's do 9 to the x plus 1. Okay, so again, I've got some exponents happening, and we don't really have any inverses to get those x's out of the exponent at the moment, but we could try our best to do what we did before, which is make two bases the same so that we can figure out what their exponents are. So again, if the two bases are the same, then the exponents are the same. So that's our goal right now. And right now, I've got a 3 and I've got a 9. So they are not the same base number, which at first can seem like a problem. You know, if the base numbers aren't the same, then we have no tools. We have no strategies to try and solve for these exponents. So at the end of the day, we'd kind of be stuck unless we had some inverse property, which we don't right now. But we can start looking at this 9. So let's look at this 9 for a second. Sure, it's not a 3 right now, but I can make it a 3. Now, a lot of us during our Zoom meeting today, we wanted to divide by 3 possibly, perhaps multiply by a 1/3, maybe take a square root. The problem with those things, and if they were great ideas because we were trying and attempting to make the 9 look like a 3. The only issue is if I divide one of these by 3, not only is it kind of tied up with this exponent up here, but I would have to divide this side by 3 as well. Remember, whatever you do to one side, you have to do to the other. And if that's the case, then now my 3 would be gone, hypothetically, completely. So we're still stuck. If I tried the idea of square rooting both sides, again, problem, because I have to do it on the left side as well. So we were trying to think, what other way can I make 9 look like a 3, but still be equivalent to a 9? So to write that out, I want the base number to be 3, but I still need it to be equivalent to 9 so that I am allowed to substitute this in, or else I'm just changing the equation and then I'm not allowed to do that. So if we think very carefully, we do have a magical little number 2, a square that would make this statement true, where I have a base number that's a 3, but it's still equivalent to 9. Okay, that way I can substitute this 3 squared into this 9. So let's do that. So now I've got 3 squared instead of 9. 3 to the x on the left side. And of course, the x plus 1, we can't forget that. That's still there. You can't just eliminate it. And then we have stuff for this. We have things to continue working with this, because right now we've got that parentheses there, and we're not used to seeing no parentheses are in this thing up here. So what can we do to make this so that it looks more like the a to the m equals a to the m? So we have our power to power rule, which we reviewed just a little while ago. Power to power, which means we multiply those exponents. So I'm going to go ahead and show that. So now I've got 3 to the x on the left. Then 3, I'm going to multiply 2 times x plus 1. Now, some of you do this all in one step. That's fine. I'm just showing each step little by little so everyone else can keep up. Okay? And I just multiplied those two exponents. Let's go ahead and simplify a bit. So now we've got 3 to the x equals 3 to the 2x plus 1. Oh, I'm sorry. Well, I almost forgot to distribute. Plus 2. Right? Because 2 times x and then 2 times 1. Now this looks like two base numbers that are the same. And then we can now compare and set equal their exponents. Wonderful. So now let me set their exponents equal to each other. X equals 2x plus 2. I'll subtract 2x from both sides in my attempt to get x isolated. Okay, let's multiply both sides by a -1. And I've got x equals -2. And I'm done. I solved for x. Now, of course, we had this extra step where we had to make 9 into 3 squared. But all it was our attempt to make, again, the base values equal to each other. We needed 3's. And since we got 3's, we were able to set their exponents equal to each other and solve for x. All right, now in case you're wondering, there is, of course, a check that we can make sure that we haven't made any errors. So let's check that together just so that you know that it exists. And if on your quiz you want to make sure you're right and check first, that's always a great strategy. So let's plug in that -2. So we've got 3x equals 9 to the x plus 1. There's our original problem. And I'm going to substitute -2 in here. So I've got 3 to the -2 equals 9 to the -2 plus 1. Okay, so I just substituted -2 for x. I'm just trying to make sure that both sides are equal to each other. That would make the statement true, and that would mean that my solution is correct. So let's start with the left side. 3 to the -2, that's the same as 1 over 3 squared. And 1 over 3 squared, that's 1 over 9. Okay, let's make sure that's the same thing on the right side. -2 plus 1, that's 9 to the -1. And then 9 to the -1 is 1 over 9. So it is in fact equal to each other. It is true, which means x equals -2 is the appropriate solution for this example. Okay? It's one of my favorite things about math. You can check them. Make sure you did it right. Let's go ahead and try another example. I'm going to go over a few more examples with you just to make sure we're all on the same page and you have as much support as you need for your homework tonight. The next two examples are coming from your textbook. So let's look at those together. So in case you're following along with your textbook, right now we're working out of section 5.3. And this example comes out of page 288. So once again, this is, we'll call this example 3. And it's coming out of your textbook section 5.3 on page 288. Again, just in case you want to look at your textbook, there are a few other examples in there. Maybe it explains in a different way that would also support your learning. It's there. Okay, so here's example this one is example 7 from your textbook. We're calling it example 3 in our notes. And it goes like this. 4 to the 2x minus 1 equals 8 to the x. Okay. So once again, we've run into a problem because we need the bases to be the same so that we can set the exponents to look the same or to be the same. So we're looking for that. Again, so that our base values are the same or equal. That way our exponent values can be set equal to each other. Okay, so that's the goal, and that is not happening here. And so we have to think, you know, let's look at the number 8. Is there a way for this base value to be a 4 and then have some exponent where it equals 8? Now it's very, very tempting to put a 2 up here because 4 times 2 is 8. So it makes sense. But 4 squared is not the same as 4 times 2, right? I think those kinds of things are really easy to miss when you're in a rush or when you think you found something like, oh, there it is, 4 to the second power, that's 8. Well, if you remember carefully, right, thinking carefully, thinking slowly, 4 squared is 16. So that's not going to work for us. So now we're kind of stuck because 4 to any power, I mean, it's never going to be 8. So that means we need to possibly break it down further. It might be the situation, right? Because right now we're looking for an 8. It might be the situation where we also need to break down this side. Okay, something so that they both have the same base, but they both yield the 4 on the left side and the 8 on the right side. And this is what I'm talking about when we're talking about these kind of puzzle-y type of problems. You need to break these down, think about them, consider the possibilities. And if you think very carefully, we know that we can use 2's, right? 2 squared is equal to 4, and 2 cubed is equal to 8. And so if we think of it that way, then we're in luck because the 2's end up being the same base, which is kind of what we're looking for here. Okay, so let's go ahead and work with those for a second. So plugging those in, or substituting them in, I should say. Instead of writing 4, I'm going to change this 4 into 2 squared. And instead of writing 8, I'm going to change that 8 to 2 cubed. Okay, and then I'm going to fill the rest in. I've got my exponent 2x minus 1 and my exponent x over here on the right. Okay, so now that I've substituted these things in, of course, I'm going to jump to my power to power rule. Let's clean this up a little bit because there's lots of parentheses. It's looking a little confusing. I would like it to look like this green a to the m equals a to the m. So let's simplify a bit. I've got 2 to the 2 times 2x minus 1, and then 2 to the 3 times x. Now I'm going to leave the parentheses off because I know all of you know that 3x means multiplication. I'm going to go ahead and distribute over here on the left so that I get 2 to the 4x minus 2 equals 2 to the 3x. Now it looks nice and clean. I've done all my steps very carefully. I followed my rules very carefully, and I now have 2 base numbers that are equal to each other. I've got 2's. Okay, and now that I've set it up nicely for myself and I've got 2's, I can go ahead and focus on the exponents here, and I can solve those. So let me drag this over here to the right side so I've got room. I've got 4x minus 2 equals 3x. I'm going to go ahead and try and isolate this x here. And there's multiple ways you can go about doing this. Some of you might have wanted to subtract 3 first so that x's stay positive. That's fine. I'm just trying to get x away from my numbers here. Okay. And with a little magic, or math in this case, I can multiply by -1, I can divide by -1, however you want to look at it. So times -1, times -1, and I've got 2 equals x. Some of you guys might have your little shortcuts for that. That's fine. Again, I'm just going through each and every little step so that our whole class can follow along if they need to. All right. So x equals 2, and we're happy. And again, we can check that. Plug the 2 into the original equation. We end up with 4 to the third and 8 squared, both of which are 64. So in case you want to check that on your own and make sure that x equals 2 is a solution, that's what we're looking for, that both sides are equal to each other. As a matter of fact, let me show that quickly, just so that we make sure that everybody's got this. So I'm going to do my check over here on the right. 8 to the 2x, well, I'm sorry, I'm reading it backwards. 4 to the 2x minus 1 equals 8 to the x. And I'm substituting my 2. This ends up 4 to the third and 8 squared, and both sides of which are 64. Okay, we're happy. You did a good job. That's a true statement. All right, so you guys are doing great. If you've been following along so far, this should take care of your homework with example 3. You should be good to go. If you'd like, stick around just for a couple more minutes, and we're going to go over example 8 from your textbook. Someone brought it up during Zoom. It was a great question. I really enjoyed working through this, and so I think you might enjoy it as well. So I'm going to continue with that example. But again, if you'd like to stop here and go start your homework, this is enough to support you with the homework that you have been assigned today, homework 9. Okay, so let's go ahead and go on with example 4. Now, example 4 utilizes a variable, or I'm sorry, not a variable, a number that some of you actually encountered during homework 7 or 8. Okay, and this number is the magical number E. Okay, so let's talk about E for a second. E is an irrational number. Okay, so let's start with that. Irrational number, which means pretty much that it cannot be represented by a fraction or a simple fraction, right? So we know another number that is irrational. We talk about it all the time. It has its own holiday, right? Our math holiday, and that's pi. Okay, so E is very much like pi in that it is a number that never ends. You've got computers still calculating it. People try to memorize decimal places for E. And in our work, we're going to be focused on the value 2.718. Of course, this continues. Just as I mentioned, very much like pi, it keeps going on forever and ever. But for our uses, we use 2.718. Okay, so E is a number and not another variable or some other complex function. E is a number, okay? Now, this number was developed by a Swiss mathematician named Leonhard Euler. So Leonhard Euler, and he was able to determine that it was equal to the limit as n approaches infinity of this awesome looking expression. Okay, you guys talked about limits. We talked about them in class before. This thing here we will be using when we talk about money in the future. It's going to look very similar. But they did some work with this and discovered that this limit approaches this never-ending number, 2.718, blah, blah, blah. Okay, this is, I suppose, the exponential function. Let me use a different color here. So the exponential function. And when I say that, I mean that E is utilized in a lot of natural things. And when I say natural, I really mean real life things. So I wasn't planning on talking about E until we started working on applications of exponential functions. In other words, real life or word problems using exponential functions. But since it came up for example 4, I figured now would be a good time to introduce it. Okay, we're going to see E when we're talking about compounding interest continuously with banks. We'll see E when we talk about growth of populations and things like that. So E is the exponential function of all exponential functions because this irrational number just so happens to represent a lot of natural real life things. So we will see it again in the future. And just remember that instead of letting it intimidate you, it is just a number, a continuous one. But you guys were able to handle pi when you were working in Algebra 2 with trig. So you'll be just fine with E. Okay, which brings us to our super exciting challenge problem from our textbook. Okay, so again, this is still page 288. And it is called example 8 in your textbook. Okay, and it looks like this. It is E to the negative x squared, and that equals E to the x squared times 1 over E cubed. Okay, so a little stressful starting out. Again, we're looking for two base numbers that are equal. That way, we can make their exponents, or we can set their exponents equal to each other. Okay, so again, I'm just writing this out over and over again so we realize, okay, this is the goal. We got to remind ourselves, these are the goals here. Okay, so right now, that is definitely not what it looks like. We've got 3 E's going on. So when all else fails, if you're looking at this and you're just thinking, I have no idea how to even begin or how to even approach this thing, it doesn't look even close to what we've been practicing, this is a completely different problem. Let's start with what we do know. Okay, let's start with, for example, the parentheses, that e to the x to the second power. Okay, let's start there, because if we can't look at the whole thing and figure out something, we can at least start with baby steps, right? So let's start with that. So left side I'm going to leave alone. There's not a whole lot happening over there. Negative x squared, okay, sure. But the right side, there's a lot going on. So let's try and clean that up first. We've got e x times 2. I'm going to write that 2x, okay? And then times 1 over e cubed. Now, some of our classmates in Zoom decided to multiply both sides by e cubed, okay, which I thought was a great idea. I hadn't thought of going about it that way, but it's definitely worth working through. You could multiply both sides by e cubed. My instinct with this one is to just continue working with this. E to the negative x squared equals e to the 2x times 1 over e cubed, right? So I just combine those fractions. And I know I have a rule here, right? My little rule, if you remember, is a to the m over a to the n equals a to the m minus n, right? We're just going to subtract them. That's the rule. Okay, just to remind everyone. So let's go ahead and do that. So now I've got e to the negative x squared equals e to the 2x minus 3. And so now I've set up my problem, just doing these baby steps, things that I already knew. I'm able to set up this problem so that I have two base values that are now the same. I've got two e's, just like we were looking for in our, our regular format that's helping us solve these equations. So now I can focus on our exponents. Okay, so yay for baby steps, all right? Here are exponents. I'm going to drag this over here. Negative x squared equals 2x minus 3. I know how much you all love x squareds. 0 equals x squared plus 2x minus 3. Okay, which means you've got a quadratic. You guys love quadratic equations. My suggestion here, some of you are very good with factoring. Go ahead and factor. Okay, that's totally fine. If you don't like factoring, my suggestion would be to use our also special b squared, negative b plus or minus the square root of b squared minus 4ac all over 2a, our quadratic formula. Okay, if you don't like factoring, become best friends with quadratic formula. Okay, we talked about this in Zoom today. Quadratic formula works for all of them. Factoring works for some, but quadratic formula works for all of them. So if you're a little bit unsure, you can use your quadratic formula, and that'll get you the same answer that we're going to get right now, which is x equals negative 3 and, or I'll just put a comma, 1. Okay, both of those answers would end up giving us the appropriate response that would make both sides of this equation true. Okay, so this one requires some more steps. It was a little more challenging, but as we saw, baby steps got us to the place we needed to be, which was here. And then we were able to solve that with some work with quadratic equations. Okay, so a lot was going on today. Lots of puzzling, lots of algebra, very slow and steady kind of work. But I'm confident that with some practice and some pacing, you guys will become very good at solving exponential equations. So just to clarify, although example 4 was quite challenging, example 3 is really what I'm going to be looking for your tests and quizzes. That's where you're showing your mastery of this type of standard. Okay, so work through them carefully. If you miss any on the homework associated with Alex, please do them over so that you can get extra points. Okay, our goal is to get 100%, and I know that you can do them as long as you dedicate the appropriate amount of time. Again, if you have questions or comments, please make sure you leave them in the discussion board on Schoology, and feel free to contact me with any concerns you might have. You know how to get a hold of me, Schoology or Remind. Thank you for always tuning into the videos and watching them through. I hope you're continuing to be safe and doing your best during this very unprecedented time of quarantine. I miss you all very much, and I hope to hear from you soon. Great job today. Bye-bye.